I get to warm myself by the notional fire. Ashley Montanaro, CEO and co-founder of Phasecraft, and we're going to talk about a piece that has got a little bit of a look in, but I think perhaps not enough. Can I get you there so I can keep an eye on questions? Thanks very much.
Thank you.
We heard from Bob Suter earlier about the software piece, of which algorithms just one part, I suppose. We're gonna hang there, which is good because I love algorithms. And Phasecraft is an algorithms company.
Mm-hmm.
If everyone has said, oh, well, you can't use your hardware very well without the software and so on, couldn't be more true, and yet we've made it all this way before really getting really into it. Here we are, though. The title of the session is Quantum Advantage Could Be Closer Than You Think. You assert that on the basis of advances in algorithms, not hardware.
Yeah, that's absolutely right. So I'm pleased to hear you say you love algorithms, because I obviously love algorithms too. And one of the reasons that I love algorithms is that we've seen in the past, like in the classical computing space, the gigantic impact that having a more efficient algorithm can have. Like the advances that we've seen from better algorithms over the last 30, 40 years far outstrip the advances coming from hardware performance. And we've seen the same thing playing out in the quantum space as well. So if you look at the improvements of various really important hardware parameters, such as gate fidelities, numbers of qubits, and so on, you'll see that over the last decade or so, maybe a bit more, they've improved by maybe a factor of 10. But what we've seen is that by developing better algorithms, we can reduce the cost of solving some really important problems, like modeling some battery material systems on quantum computers, by factors of tens of millions or more. So this can have really a far greater impact than even the other critically important task of making hardware better, which is why we think that quantum advantage is going to be much sooner than maybe some of the timescales we've heard about, which are only based on hardware getting better. We think that by making the algorithms better too, and also by coming up with really new paradigms for how to use the quantum computer, which really take advantage of its still noisy and not 100% perfect nature today, like we can really do things much sooner.
This may get too in the weeds too fast, but indulge me for a little bit anyway. What is making an algorithm better? What's the business of doing it? What are you sort of aiming for?
Yeah, so there's a number of different aspects that go into this. So at a very basic level, what you would like is you would like an algorithm that uses as few operations as possible, that uses as few quantum gates as possible, runs for as shorter depth as possible. This translates into running for as short a time as possible, but maybe more importantly than that, you, by making the algorithm more efficient, will hopefully make it just fit into the really stringent constraints that you have with today's quantum hardware. So, I always think a nice way of thinking about the way that today's quantum hardware works is that it can run for a certain period of time, and then it's like it explodes, right? You can't run any algorithms that are longer than that before they become overcome by noise and errors. So what you try to do is get an algorithm that fits into that window. And the way that we do this is through a number of different steps. So first, you have to think very hard about the specific problem that you're looking at. So this might involve thinking about the physics, the chemistry, the material science that goes into it. You then need to think about the sort of quantum information aspects that are involved as well. Like, for example, if you have a material system that you're wanting to simulate on your quantum computer, you need to encode that in terms of qubits, encode the electrons in qubits. Then you need to make the algorithm itself as efficient as possible, which might involve some automated compilation steps. And then in the end, you need to figure out the best way of getting the information out of the quantum computer as well, the best sort of measurement scheme. And then all of this, you perhaps might also wrap up in a existing workflow. So a lot of the work that we've been doing recently has been looking at plugging in quantum algorithms into a bigger classical framework so that you can firstly take advantage of all this great work people have done already over many years. And also you can just use the quantum computer for the things that it's really good at, like modeling quantum correlations, for example. And you're just using your existing classical technology to do the things that it's best at.
But there's sort of an inherent tension there, right? You want to write the algorithm that's going to be great for a computer that doesn't exist yet.
So I guess the point I'd challenge in that question is the doesn't exist yet part, because like actually, quantum computers exist and they, they're on the cloud. We can access them now. We are running already experiments on this quantum hardware, and the algorithms that we're running are very similar ones, or even the same ones that will be running in a couple of years' time.
So they're not specific. They're not they're not entirely platform agnostic, or they are.
Right. So the algorithms that we develop, they tend to be platform agnostic at a high level, in the sense that the key ideas that go into them, the theoretical physics and so on, you can translate across different platforms. But then to get the best performance out of them, you need to think very hard about the specific platform you're thinking about. So basically what we as a company are trying to do is push towards this point of genuine quantum advantage. And part of that is making the algorithms as good as possible. Part of that is obviously working with the best hardware possible and the hardware improving over time. But I would say that the algorithms that we're running now, they are already achieving, let's say, meaningful results which are comparable to some of the best classical methods that exist. But what we're trying to push towards is really having better than classical results, which we think is pretty imminent.
So you talked about the interplay between the hardware and what you were doing, but there's a third vertex in the triangle, which is the end users. Is it too early in what you're doing, what you're thinking of doing, to bring them in to sort of shape the kinds of questions you're answering?
No, absolutely not. I mean, we, as a company, for some years have been working with end users already, such as Johnson Matthey, Oxford PV, others who are experts in.
Somebody will mention their clients.
Yeah. Well, I mean, it's on our website. Yeah, you can see. And these are organisations who are really expert in particular areas where quantum computing is going to be critically important, such as battery development, solar cells. But I think that what we're seeing is that now is the time that we are really on the cusp of this quantum advantage milestone. And I'm going to, stick my neck out maybe more than others have, and say that I think that within a year from now-ish, we're going to see something which is what we would call a scientific quantum advantage milestone being met, which is quantum computing outperforming classical computing for solving a genuinely scientifically meaningful problem. I think within a year we'll get there. And I think that, companies, organizations who want to be leaders in the use of quantum computing and want to apply it to their businesses, like really now's the time to get going, because it takes, at least that long in order to really get a project set up and get some useful results from it. So I think, if you want to be a leader in this space, the time to jump in is not like 6 months after, it's like 6 months or a year before.
So now. I'm interested in the degree to which it's platform agnostic means you have a lot of potential clients who all want the best algorithm and so on. But, they're bits of maths. We all could look up Shor's algorithm, right? Like at what point does it become commercially sensitive, relevant? How do you deal with the cooperation stroke competition?
Yeah, this is a really nice question. And I think one thing that I would say the whole field of quantum computing has been marked by, which I guess is partly because of its academic roots, is a very cooperative atmosphere, I think, where different organizations, whether it's academic or commercial, are working together to get to their goals. And I think, that this is going to continue. I think, on the other hand, we are seeing that certain technologies do become proprietary. So, some of the things that we're doing, we're patenting. I mean, other people, patenting things too. Also, some of the technology we develop is not necessarily open. I mean, we think as an industry, I think it is really important to have this open flow of ideas and participation in events such as this one to share results. But I think that this does have to be balanced against the commercial needs of different organizations. So I think that there is this sort of inevitable shift to more and more things becoming proprietary.
So in the sense that you won't develop a better algorithm for one company and not another, instead you'll patent it and license it to whomever wants to pay the cost.
This is certainly a possibility. Yeah. I mean, I think there are different models which make sense depending on industries, different industries, depending on what different partners are looking for. There are some who really want to be the only one in their sector that is getting the quantum advantage, and they may have different priorities than someone who, they want to have leading technology, but they don't really care about whether another organization has it as well. And so I don't think it necessarily has to be one size fits all at the moment anyway, because we're still, at this sort of dawn of the quantum commercial sector. And I think that we'll see a number of different models coexisting.
At the mention of partners and sort of how it works, and we've talked so much about hardware and how people do or don't understand what's available to them and whether it's useful for them and so on, where the sort of, if you like, education sticking points are. What are the education sticking points when it comes to algorithms? When you talk to partners, potential partners, new clients, people in the space more generally about this, what are the mistakes people make, misconceptions they have?
I think there's a couple of key things that we say a lot to people. Like the first one is, if I can think of at least three. The first one is one which probably many people here know, but I think it bears repetition, which is that a quantum computer is not just a faster classical computer. You can't run your classical algorithm on the quantum computer and make it run faster. In general, quantum computers are physically slower than classical computers. You need to come up with a new algorithm to run on it, which is special and takes advantage of quantum mechanics. And
I'm sorry that we're still there. So
yeah,
at that early stage.
Yeah,
okay.
Yeah. I mean, in my previous role as professor of quantum computing at university, and so I've been saying this to people for many years, but it's I think it still bears repeating. Then I think there's the point that quantum computers are not good for really big data problems. I think in general, this is again a misconception that quantum is going to be useful for solving problems which we can kind of solve now, but we just can't run the algorithms quickly enough because we've just got too much data to run it on. This is almost the opposite of the sort of problem domain in which we want to run quantum computers. I think the sort of application domains where quantum computing will be genuinely useful is things like modeling quantum physical systems, like materials, batteries, solar, catalysts, and also solving hard optimization problems. So.
With the limited time we have left, I've been asking this question of various people for a really long time. It still interests me a lot. You say the era of advantage could be closer than you think because of improvements. Improvements in algorithms, not discovery of new algorithms. I'm interested in that question in particular because it could really change the scope of kind of what we're all aiming for here. Can we imagine? Can we dare to imagine that there are algorithms out there that will open up entirely new problem classes?
Absolutely. I would be shocked if there aren't actually any such algorithms.
Oh, it's like aliens. They exist.
Yeah.
Will we find them?
Yeah. So I think
I assert.
I think we will, and I think again a sort of bugbear of mine from my time in the field is there is often this assertion that there are very few quantum algorithms out there, and I would claim there are actually quite a lot, and also people are coming up with genuinely new ideas. I mean, I'll mention, for example, this DQI algorithm from Google, which came out a few months ago, which is a new approach to solving certain optimization problems efficiently on a quantum computer. And people are also coming up with new ways of applying quantum computers within other workflows. And, we came up with a new way of combining quantum computing with density functional theory, which is, the real workhorse for materials and chemicals modeling. And I think it's this kind of combination which in the near term is really going to be the kind of new idea that does unlock practical applications. I'm
24 seconds over, but I want to push this just a little bit further. Sure. All due respect, that might sound to the untrained ear kind of incremental. I mean, holy crap, we discovered an entire new kind of problem, kinds of businesses we can help, kinds of problems we can solve, kinds of, biomedical applications, what have you. Do you see an entirely new paradigm shifting kind of thing in terms of algorithms that sort of arise in that mathematical brain?
Yes. I mean, and I think, as you say, it's not, this kind of breakthrough discovery is not something you can put a timetable on. But what I would say is that it would be kind of almost unimaginable to me that we have this amazing new technology and there's nothing we can do with it beyond the things that we happen to have figured out we can do before we even got our hands on someone like really high performance, advantage level versions of this technology. I think also people often, I think, ask somehow more of quantum computing than they would of classical computing in this context, because how many breakthrough applications have there been in classical algorithms? Like, I mean, maybe those here who are not computer science professors may not be able to think of that many algorithmic breakthroughs which have really changed our everyday lives. And yet, today's classical computers are incredibly valuable and are, it's unimaginable to think of life without them.
Right. So everything else is gravy, is what you're saying.
Exactly.
Very good. Ashley, thank you very much for your time.
Thank
Appreciate
you very
it.
much. Thanks.